Let us start. So in the previous lecture, we started to construct the theory of scalar particles using the first principle approach. That means using the Lagrangian and the canonical quantization. We started from the most general Lagrangian L, which depended on two possible invariants which can be built from scalar field, namely the field itself and the value x, which was the square of the derivatives of this scalar field. And we have found that up to field redefinition and up to quadratic terms, we obtain the most general form of such a Lagrangian as some constant, lambda 0, plus so-called kinetic term and so-called mass term. Here we are able to go to the Hamiltonian formalism, introducing the generalized momentum pi, which was just given by partial derivative of the Lagrangian with respect to the time derivative of the field. And we just obtain that this generalized momentum is just the time derivative of the field. And then we constructed the Hamiltonian as a Legendre transformation of the Lagrangian with respect to generalized velocities. That means to these time derivatives of the fields. Namely, we obtain such a formula. And here was something which we called phi omega squared, phi, where this plus other term, where this omega squared was operator which was given by the Laplacian plus m squared. And we encounter the first divergence in our theory was the infrared divergence, which corresponded to the large distances, large wavelengths, or small momenta in the momentum space. And we decided to regularize this infrared divergence, since this omega 0 was constant, using the finite box in which we closed our system. So, in fact, our regularized version of this last term was just the limit for v goes to infinity of v times omega 0. Okay, we have Hamiltonian, and from the Hamiltonian we obtain the evolution equation for our pi and phi as a Hamiltonian equation, and using the canonical quantization procedure we obtained that we have to replace these classical fields phi and pi by operators. These operators should obey the canonical commutation relations, symbolically phi commute, pi commute, and phi x, pi y commute to I delta 3 x minus y. We suppose that we have some representation of these canonical commutation relations on some Hilbert space up to not specified, which is up to now not specified. And we suppose that the evolution equation, time evolution equation for these Schrödinger operators in the Schrödinger picture of these phi's and pi's. That means the evolution equation for Heisenberg version of these operators. That means, for instance, this phi x is just e to I h times time, phi x e to minus I h tau was the usual Heisenberg equation of motions, namely phi dot is just 1 over I, commutator of phi x with the Hamiltonian, and pi dot x is just 1 over I, the commutator of pi with the Hamiltonian. Here, this phi x are in fact the Heisenberg operators, which depends on time, and x are given by this formula. Sorry, it should not be this. So these are the Heisenberg operators. Whenever I will use the notation phi x, I will mean the Schrödinger picture, time-independent operator in the Schrödinger picture of the time evolution. And whenever I will use such a notation without any arrow, I will have in mind the Heisenberg operators. That means time-dependent operators in the Heisenberg picture of the time evolution. And we have found that these two equations are equivalent to the Klein-Gordon equation for the field. And we have the canonical commutation relations at equal times. And we know that provided these two ingredients are satisfied, then these operators phi x, the Heisenberg operators, can be expressed as a linear combination of creation and annihilation operators. This was proven in one of the previous lectures. Where provided we suppose that this field is Hermitian, these two operators are Hermitian conjugation one of each other, and that using the canonical commutation relations, we can obtain the commutation relations for boson operators, namely these annihilation operators and the creation operators commute, and the annihilation operators with the creation operator commute to the invariant delta function k minus k prime. And provided we suppose the Fock representation of these canonical commutation relations, that means the existence of vacuum state, which is annihilated with all the annihilation operators, and provided we have a basis of our representation space simply obtained by acting these creation operators on the vacuum state, and provided this Hermitian conjugation is satisfied, then we have complete representation of our fields on the Fock space of particles which are characterized by its momentum p and nothing else. These are unparticle states. But in this Lagrangian, there are also other ingredients hidden, namely the nether currents corresponding to space-time symmetries. We have only discussed the Hamiltonian yet, but there are also other, namely the momentum operators. For instance, these momentum operators are given by the formula minus integral d3x pi x gradient phi x. The rotation generators, therefore the operators which can be taken as angular momentum operators. These are given by such a formula. Also the generators of the boost, which are given by this formula. And we started to discuss these operators as the operators on the Fock space. We have found that these operators depend on non-commuting operators pi and phi, and therefore there could be some problem with the operator ordering in order to get from these classical expressions the operators on the Fock space. But we have found that there is no such a problem, in fact, since the only difference between two possible ordering or several possible ordering of these operators comes from the commutators of pi and phi, and these are the pure numbers. Since we have such a canonical commutation relations, there is an identity operator on this right hand side, and therefore the commutation relations of any or ordering of these these operators in any ordering will not depend on this operator ordering, in fact. So it is an exercise which I leave to the seminar to prove this. So, for instance, you can take so-called pi phi ordering. That means all the pi's on the left on all the phi's. So simply take these formulas and insert in these formulas. In these formulas for these classical pi's and classical phi's, they operator forms, and take the pi's on the left with respect to all the phi's, and it can be shown, and you will probably do it during the seminar, that if you, for instance, calculate the commutator of this phi pi with the translation generators, with the three momentum operators, you obtain just minus I gradient of this phi, and this is just the correct way how to transform the scalar field with respect to translations. Similarly, if you do such a commutator with the generators of rotations for the angular momentum operators, you obtain just minus I x cross nabla acting on this phi. And again, this is the correct transformation property of the scalar field with respect to infinitesimal rotations. You can also try to calculate this commutator with generators of boosts, and what you get is just minus I x times pi plus t times gradient phi x, which can be written, because we know this pi is just the time derivative of phi, in the form of minus I x time derivative of phi x plus gradient times t acting on this phi. And again, you can recognize in this right-hand side the proper transformation property of the scalar field with respect to the infinitesimal boosts. And you can also find that all the generators P mu and the corresponding generators J mu obey the Poincaré algebra. So in this way, using the Noether theorem and promoting the classical expressions for the conserved charges or conserved observables to the operators on the Fock space, you completely reconstruct the generators of the space-time translations, rotations, and boosts on our Fock space. And since these relations are just infinitesimal forms of the finite transformations with respect to Lorentz transformations, namely these formulas, you can obtain by exponentialization of these infinitesimal relations the valid transformation properties of the scalar field with respect to this unitary representation of the Lorentz group, namely the representation of the Lorentz group, which is just exponential of I half omega mu nu. These J mu nu, these J mu nu are just J's and N's. And with respect to the translations, which is given by exponentialization of I times parameter A times the generators of times translations. So in the Lagrangian formalism and using the canonical quantization, we were able to reproduce a lot of ingredients of our theory, which we previously obtained by the bottom-up approach, the Weinberg approach. Namely, we obtained the canonical commutation relations. It was the prescription for the quantization. We obtained the Klein-Gordon equation. We obtained the Bose canonical commutation relations for creation and annihilation operators, and the Fock representation of them. And we also obtained the representation of the Poincaré group. Okay, what remains? It remains to show that this representation of the Poincaré group have the required property, namely that the Fock vacuum state is invariant with respect to Poincaré transformations. Let us illustrate this problem with the time translation invariant. Therefore, time translation invariance. Therefore, let us show that appropriate choice of this remaining free parameter in our Lagrangian, namely this constant term, omega 0, we can arrange for Poincaré invariant vacuum, time translation invariant vacuum. For this, we will need to show what is the Hamiltonian when expressed in terms of creation and annihilation operators. And these form the basis on our Fock space. And when we know the expression of H in terms of creation of annihilation operators, we know how it acts on the basis vectors of our Fock representation, namely how it acts on the ground states, on the Fock vacuum. So let us remind you that this Hamiltonian is just such an integral. Now here will be the operators pi squared, and I probably will rewrite it in slightly different form. 1/2 gradient of phi times gradient of phi plus 1/2 m squared phi squared. And we have also here this infrared divergent term. Let us omit this sign of limit. We suppose that we closed our system in finite dimensional, finite volume v times this omega 0. Well, in order to express this Hamiltonian in terms of creation and annihilation operators, and let us remind you that there is no a priori problem with operator ordering in this A, since all these terms are functions only of pi or of phi, and therefore the terms here all commute, and there is no problem with operator ordering. So in order to have this expression in terms of creation annihilation operators, we can use the expression of the field phi. And since this operator, even if these operators were Heisenberg operators, will not depend on the time, since the Heisenberg operators obey the Klein-Gordon equation, and the conserved currents or conserved charges from the Noether theorem do not depend on the time, provided the fields obey the classical equation of motions. Therefore, we can use any time in order to calculate this Hamiltonian, and we will choose the time x0 equals to 0. So in fact, our operators will be the Schrödinger operators, since the Heisenberg operators at x0 equals to 0 coincide with the Schrödinger operators. So let us calculate. Let us calculate this, and we see that this is nothing else but this invariant measure times annihilation operators. Now here is only the 3 vector scalar product plus sign plus the Hermitian conjugation of this. That means e to minus I k times x. And we can also simplify this using in this second term the substitution k goes to the minus k, with respect to which the measure is invariant. And the 4 vector k, therefore, is substituted with vector k tilde with the inverse sign, the special components of this 4 vector. So we can write this as integral k times e to I k times x times sum of the annihilation operator at k and the creation operator at the k tilde. Similarly, we can calculate this pi. We know that pi can be obtained from in the Heisenberg picture as derivative of the phi in the Heisenberg picture, and we can take x0 equals to 0 to obtain the Schrödinger representation. So this Schrödinger representation will be just obtained from derivative of this formula with respect to time. So what we get is just integral d tilde k, and here we obtain minus I k0. K0 is just the relativistic energy k times a k. Putting x0 to 0, we obtain here just the exponential with only 3 vector scalar product. And the second term will be plus, since there is a change of sign, I, again, the relativistic energy, times a cross k times e to minus I k times x. And again, for further convenience, we make a substitution k to the minus k in the second term, and we can rewrite this pi x just as minus I integral d tilde k times ek, since this relativistic energy is invariant with respect to this change of variables. And what we get here is just a k, and to take into account this minus sign, minus a cross k tilde. So this is our expression for phi and pi. And now we should insert this in our Hamiltonian and evaluate some integration and so on. I will not do it completely. I will show you only how to obtain this first term. That means let us calculate just integral 1/2 of integral d3x times pi squared x. So what we get is square of this expression. So we obtain just minus 1/2 and 2 powers of pi. That means let us denote the integration variable of the first pi as chi, the integration variable of the second pi as q. And what we get here is just ek eq times a k minus a cross k tilde times a q minus a cross q tilde. And this should be integrated over d3x. And what remains here are these exponentials. Sorry, I have forgotten to reproduce this exponential here, so there should be, of course, such exponential. Sorry. So only dependence on x is in these exponentials. One is with 3 momentum k, the second is with 3 momentum q, so we get here just k plus q times x. Well, now the integration over the x is trivial, since here we obtain the integral representation of the delta function if we integrate over these 3x, and we obtain just minus 1/2 times d tilde k, d tilde q, ek, eq, times 2 pi to the 3rd power times 3-dimensional delta function of this k plus q. And what remains is just this product of the differences of creation and annihilation operators. Now it is easy to take the integration over, say, q, since we have to simply replace the q with minus k. So what we obtain here is just minus 1/2. And I remind you that this measure, invariant measure dq, is the ordinary measure d3q over 2 pi to the 3rd power times 2 eq, the relativistic energy. So we cancel this relativistic energy. We cancel these 2 pi's, 2 pi to the 3rd, and the only effect is just, as I said, the substitution for q minus k. So we obtain here integral over d tilde k times 1 remaining k times just this a k minus a cross k tilde times a, and since we substitute for q minus k, therefore for q we should substitute q k tilde. Sorry. So here will be k tilde minus a cross k. Well, this is the resulting expression, and similar expression can be obtained also for the second term, depending on phi, this term. I leave it as an easy exercise to you, and I will only quote the result. And the result is just, sorry, I have forgotten this 2 here, so instead of 1/2, in this resulting formula, there should be 1/4. And similarly, the term 1/2 integral d3x, we have this gradient phi squared plus m squared phi squared, is given by plus 1/4 integral d tilde k ek. And now I remind you that this phi is given by sum, not a difference between creation and annihilation operators. So here will be also the sum. The mechanism of appearing of these tildes here and here is the same as in the previous case. So in order to get the complete Hamiltonian, we should add these 2 expressions, this one and this one. And we can easily see that if we elaborate this multiplication brackets, we see that the diagonal terms, that means the terms ak, ak tilde, appears in both these expressions, but with different sign. Here is minus, here is plus. Similarly, this diagonal term a cross k0, k tilde times a cross k, appears also in this expression, namely this, but here with the different sign. So these diagonal terms will cancel each other, and what remains are the terms which are mixed. Therefore, one annihilation operator, one creation operator, here and here, and the same in this second case. These add together, and what we get in the end is that we obtain twice these mixed terms. So the Hamiltonian will be, instead of 1/4, it will be 1/4 times 2, that means 1/2, integral over d tilde k times this ek, and the mixed terms. And as you can see in the mixed terms, either both arguments are k's or both arguments are k tildes. And in the second term, which depend on case tilde, we can again return back to the k, simply again doing the substitution k goes to minus k. So we can summarily write this Hamiltonian as simply A cross K, A, K, plus K, A cross K. And of course, we cannot forget the constant term, which we have written as, there should be some minus sign probably I have written here already, here, not correctly. It should be minus in Lagrange, since in Lagrangian is with plus and the Hamiltonian is Legendre transform. So here should be minus. And this additional constant term, which has infrared divergence in it due to infinite volume, times this omega 0. Okay, so this is the expression of the Hamiltonian in terms of cohesion and annihilation operators. So now we know how this Hamiltonian will act on the vacuum, and we can make also some arrangement of these terms to make this action on the vacuum even more manifest. Simply using canonical commutation relations for the bosonic operators to rearrange this term. Simply we can write this term as AK, A cross K commutator plus the inverse order. That means A cross K times AK. Well, so we obtain that the Hamiltonian is 1/2. Sorry, this 1/2 will be cancelled since we obtain this term twice. Here will be just A cross K, AK, and also the commutator. And this commutator is just the invariant delta function explicitly 2 pi to the 3rd power times 2k times delta function, delta 3, but now delta function k minus k, that means delta function 0, and minus v omega 0. And there is something wrong with this expression, since what is this delta function? This delta function was the delta function in momenta, so we can take it as a limit. K goes to 0 of delta function in momenta, and therefore we can rewrite it as 1 over 2 pi to the 3rd power times integral, used integral representation of the delta function d3x. We can limit for k goes to 0 e to I k times x. And we have encountered already such an integral. We see that in the limit of when k goes to 0, this is infinite. And we can regularize it again by closing our system in finite volume. So we regularize this integral over d3x over finite volume times 1 over 2 pi to the 3rd. Therefore, we will write it regulated, infrared regulated version as v over 2 pi to the 3rd. Okay, so inserting this in the Hamiltonian, we obtain the following form for it. Here is the term A cross K, A, K, plus something which is proportional to the volume of our system. Let us write it V, and let us add these two terms proportional to the volume, this one and this one, to some common value curly E0. Well, what is the meaning of this curly E0? If we take the vacuum, the ground state, and calculate the mean energy of this ground state, we obtain just sandwiching this first term with vacuum, we obtain 0, since this annihilation operator will act on the vacuum. And of course, the vacuum is annihilated by the annihilation operator. So the only contribution will come from this second term. So this will be V times E0, or stated differently, if we calculate the energy density of the ground states, that means the limit for V goes to infinity from this mean energy of the vacuum divided by V, we obtain just this curly E0. So this curly E0 is the energy density of the ground states, over the ground state of the vacuum. But what we know, or what we demand for our theory. We don't demand for our theory that the vacuum is invariant with respect to the Poincare group, namely Hamiltonian on vacuum should give 0, since the time translation are generated by Hamiltonian, and therefore the only possibility how to obtain invariant vacuum with respect to translations is that the generators of the translations annihilate the vacuum. Therefore, not only Hamiltonian should annihilate the vacuum, but also the free momentum, means the generators of spatial translations, should annihilate the vacuum. So the physical requirement in our theory is that the energy density of the ground state of the vacuum should be 0. Of course, in fact, you can argue that physically this E0 is not measurable. What we can measure is only the excitation above the ground states. Therefore, the differences of the excited levels with respect to this ground state energy. But to have invariance of the vacuum with respect to translations, we need to require this energy density of the vacuum to be 0. It can be changed in the case when the theory will be coupled to gravity, for instance, and we know that there is a cosmological constant that is just plays the role of the energy density of the ground states, and it is this cosmological constant is important for the gravity coupling to the matter. But in our Lorentz invariant and Poincare invariant theory, this is the requirement of the invariance of the ground state. So we see that this E0 can be calculated in some sense in our theory. We simply see that E0 is just this minus omega 0. This was the constant term in the Lagrangian. This is this part of the Hamilton, and also the term which comes from this. And what is this? This is simply the integral over d3 dk tilde times this ek squared, okay, here, therefore times, sorry, there should be 1/2, we have forgotten this 1/2 here, so this 2 is cancelled, so we get here this ek squared, and this is all. So again, using the explicit form of our invariant measure, we see that this is nothing else but minus omega 0 plus 1/2 integral d3k 2 pi to the third survives times ek. And we easily see that this integral is divergent. This divergence is called ultraviolet divergence. We have encountered such a notion the previous lecture, and we can regularize this divergence by cutting off the large momenta in this integral. So we can calculate regularized vacuum energy density as minus this constant omega 0 plus say 1/2, and we simply cut off the large momenta, taking them small in absolute value than some fixed scale lambda. And we see that the leading singularity of this expression when lambda goes to infinity, since in the end we should put lambda to infinity to remove the cutoff, to remove the regularization, we see that this can be calculated simply for large omega. We can write this as an integral, since this regularization is rotational invariant. We can use the integration over the angular variables. We obtain here 4 pi times k squared over 2 pi to the third. And provided we are interested in the upper end of this integration, we integrate here from 0 to infinity, not to infinity, but to the lambda, we can, provided this lambda is much, much smaller than the mass of the particles, Then we can replace simply, in order to get the leading order in lambda of this integral, this ek by just k. So this can be easily calculated. And as a result of this simple integration, we obtain just minus omega 0 plus this cutoff lambda to the fourth power, here is the fourth power, and over 4 pi to the second power times 1 plus something which behaves like 1 over the cutoff. So we have seen that if we calculate in our theory the regularized energy density of the vacuum, we obtain something which diverges as the fourth power of this cutoff scale, as the fourth power of this cutoff scale. Then we try to remove the cutoff, then we to send this lambda to infinity. So the theory gives infinite result for something which have clear physical meaning. It is the density energy density of the vacuum. So what we can do to heal this problem? The only possibility is to prescribe this omega 0 as something which in fact depend on our regularization scale in such a way that the divergence of this omega 0 completely cancels the divergence coming from this expression for our regularized contribution to the energy density. This procedure is known as renormalization procedure. And we will meet this renormalization procedure later when we will assume the interactions and when we will assume so-called loop graphs. But we see that already at a completely free case, we are describing free particles which do not interact. There is a renormalization problem connected with the energy density of the vacuum. And this renormalization procedure can be described in several steps, as we did here. First, we would like to use our theory to calculate some physical quantity. So we can, in practice, meet some ultra-well divergences. So we first regulate them. So we choose some regularization of UV divergences. In our case, this was the momentum cutoff. But there are many other possibilities of regularizing these UV divergences. Then we should add to our Lagrangian so-called counter terms. That means the terms explicitly depend on the cutoff scale, on the regularization scale, in such a way that the resulting physical quantity will be finite when this cutoff is removed. That means that we have first identified the UV divergent contributions. Sorry. And add so-called counter terms, which are cutoff independent. Sorry. In such a way that these contributions of these counter terms cancels the divergences. But there is one problem. As we can see, what we need is to completely remove the powers and logarithms of this cutoff scale. So the fourth power, the third power, the positive power of this cutoff scale, and logarithms of this cutoff scale. But we have no guide how to take, so we using the concrete regularization procedure, we know how the UV divergent part of this counter term should look like. But we do not know the finite part of this omega 0, for instance. So this procedure is ambiguous. We do not know how to fix finite parts of the counter terms. In our example, we simply can take this omega 0 as just this lambda to the fourth over 4 pi squared plus some terms which cancels the third power, some terms which cancels the second power, some term which cancels the first power, and some terms which cancels the log of lambda. But we can add at our will completely arbitrary, say, omega 0 constant, which is not fixed by this procedure of destroying the UV divergences. So there should be some physical principles. Sorry, I'm not able to switch the pen. Which tell us what this finite part of the counter terms should be. And this is the called normalization condition, which is physically motivated to fix the finite parts of the counter term. In our case, this was the requirement, in our example, this was the requirement that epsilon 0, the energy density of the vacuum, should be 0. So we simply take this omega in our regularization scheme, dependent on this lambda, exactly to cancel all the divergences and all the finite parts of this integral. Therefore, this omega is just this 1/2 of the integral cutoff times k. So this is the first place where all the principles of the renormalizations come into the game. Not only regularization in order to regulate the divergences, not only identification of the infinite part of our calculation, not only cancelling this infinite part by the cutoff dependent counter terms, cutoff dependent constants, but also some normalization conditions which are physically motivated and which allows us to fix the finite part of the counter terms. And these normalization conditions define so-called renormalization scheme. Okay, so this was the reason why we keep this omega 0, something which was from the first side completely unnecessary in order to reproduce all the other ingredients of our canonical quantization in our original Lagrangian. Simply, we have to include in our Lagrangian all the possible terms which are allowed by the symmetries and the other requirements to this Lagrangian, and keep all of them, since we don't know whether some of these terms will not be necessary as counter terms when we will calculate some physical quantities. This was the case of this omega 0, which was revealed only when we calculate the energy density of the vacuum. Fine. So our renormalized Lagrangian, Hamiltonian, with this special choice of the omega 0 and taking then the lambda to infinity, we can do it now since we have cancelled all the ultrafile divergences, is just given by the simple formula d tilde k, ek, a cross k, ak. Remember that this was what we get from the first principle, from the bottom-up construction for the Hamiltonian, using the construction of the Hamiltonian in terms of symmetry acting on particle states and so on. But we can rewrite this Hamiltonian also in a slightly different form, using the new so-called normally ordered product of operators. Simply, in our theory, we have fields, we have canonical momenta, which are in Heisenberg picture given by the derivative of the fields. And we encounter frequently the monoms, which are simply some object constructed from these fields or from this derivative of the fields and so on. Simply, we will concentrate ourselves to the case of such monoms. There should be also powers of this pi, y1, pi, ym, and so on, even some derivatives of this fields and so on. We will see that everything is hidden in such monoms, since derivatives and pi's are given in terms of derivatives of the original fields. And the normal product of such operators is usually denoted by this semicolon, and whatever else is inside this symbol is defined in such a way that we express this product in terms of creation and annihilation operators, and then any such monom in creation and annihilation operators ordered in such a way that all creation operators are on the left with respect to all annihilation operators which are on the right. Example, our Hamiltonian, we have found that if it is expressed in, it is some product of phi's, some product of pi's, some product of derivative of phi's, everything can be expressed in terms of creation and annihilation operators, and we in the end obtained just 1/2 d tilde k, and here was k, and a cross k ak plus ak a cross k plus this minus this v times omega term. We see that this is not ordered in such a way that all creation operators are on the left and all annihilation operators are on the right, since this term doesn't satisfy this condition. So the normal product of the corresponding fields entering in this Lagrangian is expressed in the ordered way. So this first term is without change, and the second one is changed in such a way that we suppose as if these two operators commuted and simply write the creation operator to the left and the annihilation operator to the right. Therefore, it is nothing else but 1/2, sorry, not 1/2, d tilde k times ek times this a cross k ak. This is the general procedure. Simply express all the products in terms of creation annihilation operator, and then forget about the fact that the creation annihilation operator do not commute, take them as commuting, and arrange the resulting expression in such a way that all the creation operators are on the left and all the annihilation operators are on the right. So we see that provided we use for our operator h the normally ordered prescription, therefore if we substitute for all the products of the operators the normally ordered products, so if we go from h to normally ordered h, we can completely forget about this omega 0. We can write our renormalized Lagrangian, this one, simply as the normal ordered product, is H renormalized, is just the normally ordered product of the original Lagrangian d3x 1/2 pi squared plus 1/2 gradient phi plus 1/2 m squared phi. Since we have found that this part is just this 1/2 integral d tilde k ek times this a cross k ak plus opposite order ak a cross k, and as we have seen, this normal ordering results just in expression where all the creation operators are on the left with respect to all annihilation operators. So our renormalized Hamiltonian, which yields 0 density of the ground states, can be simply obtained by expressing the original form of the Lagrangian not in terms of ordinary products of operators, but using the normally ordered products. Fine. So the normal ordered products is some special products of the operators, and it has some very interesting properties which will be useful for us and which will be used very frequently when we will deal with interactions in the Lagrangian. So we see that the problem of translation invariance of the ground states, the problem with 0 energy density of the vacuum state, can be solved using the normal ordered products instead of the ordinary products. And using the ordinary products, you can completely forget about that annoying eta 0 term in our Lagrangian. We can repeat this kind of reasoning also for other operators which you have constructed as a product of, say, phi's and pi's, namely for the generators of translation, generators of rotations, or the angular momentum operators, and for the generators of boosts. But we have seen that since these operators are bilinear in creation and annihilation operators, the difference between this new ordering of the operators, that means using the normal order products instead of the ordinary products, will differ from our previous way how to order the operators only by some multipliers of identity operators, and this will not change the commutation relations of these operators with phi's and pi's operators, and therefore the corresponding representation of the Poincare group acting on the creation and annihilation operators and then on the particle states will be the same. So there is no problem with operator ordering. But the advantage of the normal ordered prescription for these operators, that means for using normally ordered products of the operators when we pass from the classical expressions to the quantum operators, is that automatically the normally ordered operator P, normally ordered operator J, and normally ordered operator N give the vacuum invariant, since the vacuum will be annihilated with all these operators, and therefore we will not need any counter term to satisfy the requirement of Poincare invariance of the vacuum. So using the normally ordered form of our operators is something like implicit renormalization. Implicit renormalization in the sense that we set this counter term, for instance, this omega 0 to 0, and normal ordering automatically removes all the ultraviolet divergences without need of any necessary counter term. Well, we will spend now some time just with this normal ordered products, since, as I have already said, it will be very important when dealing with interactions. So you will have to survive some boring mathematical theorems concerning this normal ordering. Well, so let us enumerate some basic properties of normally ordered products of operators. Simply, if we have some operator which is a monom or some functional of operators, and if we take instead of ordinary products the normal products in this expression, it is easily seen that if we calculate the vacuum value of such a functional, we obtain simply 0, since all the creation operators are on the left, all the annihilation operators are on the right, and either these annihilation operator on the right annihilate the vacuum, or these creation operators on the left annihilate the vacuum. The only exception is the trivial operators O, which are some C numbers times identity operators. This is the only exception. The second feature of this normal order product is that this normal product is commutative. Simply, if we have, for instance, two fields, phi x1, phi x2, and take this product as normally ordered product, it is the same as we take it in opposite order. Simply, in both cases, we express first this expression in terms of creation annihilation operators, and then completely forget about the non-trivial commutation between creation and annihilation operators, and freely remove or move the creation operators to the left and the annihilation operators to the right. And this procedure is the same, provided we start with such a order of the fields and such order fields. So the normal product is commutative. The third feature of the normal product is that if we have some normalized states, say some states psi and phi, which are normalized, say norm of these finite, we can take this finite constant as 1 by proper normalization of these states. Then, if we take some matrix elements between these psi and phi of any normally ordered operator, that means the operator in which we use the normally ordered product, then this is finite. This matrix element is finite. You can understand this simply as the fact that this, for instance, psi or phi state is some wave function phi k1 kn times some string of creation operators, acting on the ground state. And if this operator is normal product, there are some string of a's on the right, some string of a crosses on the left, and this a's can be commuted to the end of this string acting on the vacuum and giving 0. And during this process of commuting, we simply generate some delta functions, but these delta functions are smeared by this function phi, this wave function phi, which is supposed to be integrable since the state is normalizable. So there is no problem with this commuting all these a's through this creation operators. There is also no problem with similar commuting all these operators to the left and let them act on the ground states on the left to obtain 0, since again we produce by this procedure some delta functions, but these delta functions are saturated by the integration and smeared by the corresponding wave function corresponding to the phi. So there is no source of infinity in such a case, provided there would be at least one combination A cross in not normally ordered operator. Then we should either commute this A to the end through this operator A, but this operator has no smearing these operators in the case of normal operator Z. So this will produce some delta function which is not smeared. So in the case of not normally ordered product, we can expect the presence of some delta functions. Of course, the result can be finite, but it is not the usual case. So the normally ordered operators have the advantage that when we calculate matrix elements of such normally ordered operators in normalizable states, the result is finite. And let us give some formula which will be frequently used in our next lecture. And this is the formula of the normal ordered product of two operators, phi x and phi y. Remember that these operators can be rewritten as the so-called positive frequency part and negative frequency part. This part corresponds to the annihilation operators. And this part corresponds to the creation operators. So if we would like to write normal ordered product, we should simply elaborate this product. So we obtain just phi plus x, phi plus y, plus phi plus x, phi minus y, plus phi minus x, phi plus y, plus phi minus x, phi minus y, and normally order this. Well, this is the annihilation operator and annihilation operator. This is okay. There is no change by normal ordering. This is the annihilation operator and creation operator. This is something wrong. We should rearrange this. This is the creation operator. This is the annihilation operator. This is in nice order with respect to normal ordering. And this is the creation operator and creation operator. This is correct. So the result will be just reproducing these terms and rearranging this one. So the difference between the normal ordered product, phi x, and phi y, is just what we do here. Simply remove this offending term and replace it with the right term where the creation operators is on the left and the annihilation operator is on the right. And we see this is nothing else but phi x, phi y. And here we obtain just minus commutator of phi plus x, phi minus y. And this commutator we have already calculated. This is nothing else but the function delta plus x minus y. So we have the following formula for normal order, the ordered product of two operators, phi x and phi y. It is the ordinary product, phi x, phi y, minus I, this function delta plus x minus y. This formula will be important for us since it will allow us to express the ordinary products in terms of normal products, which, as we know, have some pleasant property, namely the regularity and zero vacuum expectation value. Okay, so we have run out the time, so I will stop here.